Now my problem in this instance is to compute t. And before I can compute t, I'm going to have to compute s squared. But let's first look at t. It's the same blooming formula in form. T sub nu, that nu's on there to indicate I have to pick up a particular t distribution. And that nu is fixed by whatever number of degrees of freedom are in s squared. So you notice there's a similarity between these two formulas. Here's the original formula for the normal deviate, where we had sigma squared underneath the square root sign. Here we have s squared under the square root sign. And of course what you see here are two forms, two expressions, sigma squared over n, or 1 over n times s squared. They're obviously equivalent. What I'm going to do now is substitute in this equation for t, the values we currently have. Now let's see, y bar, as I remember, turned out to be 30. And the hypothesized value of the mean is 28. Just plugging along here. The estimate of the variance, you remember, was 32. And n was equal to 5, so it'll be 1 over 5. And that will generate a t with how many degrees of freedom, gang? How many degrees of freedom will that t have? Well, you answer that by saying how many degrees of freedom does the s squared have? It has 4 degrees of freedom, so we're doing a t with 4 degrees of freedom. Okay, let's look at a t distribution with 4 degrees of freedom and see what comes out. But before we do, we better solve this blooming equation. So let's go ahead and solve it. Let's say that t with the 4 degrees of freedom in this case comes out to be equal to 0.8. Just to refresh your memory, however, before I leave the board here, to remember how you go about calculating s squared. How did I get s squared in the first place? And the method by which I use to get s squared is I evoke the following formula. You can go ahead and get the estimate of the variance by using this particular formula. So to get that 32, which I substituted there, right, we might go through the details of that calculation now while we have an opportunity. So before we look up the critical value of t, let's review very quickly and find out how we picked up that particular value of s squared. So I'm going to go back to the board and do a quick job of getting the estimate of the variance here based on those 5 observations, and I'm going to take advantage of that particular equation that you see right there. And over here, there are the observations. 24 observations total to 30 with an average of total 150 with an average of 30. Now from each observation I've subtracted 30. You see, 36 minus 30 is 6, and so on down the line. These deviations have summed to 0, as you recall they must. Then we've squared the deviations, 36, 36, and so on. The total is 128, and now you see me in the process of getting the estimate of the variance. And the estimate of the variance is 128. Now, you notice the number there is missing. What in the devil would you divide down by to get the estimate of the variance? And the answer is n minus 1. There were 5 observations. There are going to be 4 degrees of freedom, and so I would divide 128 by 4 to get the estimate of the variance, 32. So dividing by 4 gives me a 32, and of course that's an estimate of the variance based on 4 degrees of freedom. Okay, now back over on the board here, you've seen us insert that particular estimate of the variance, 32, and go through and turn the crank and grind out the express value of t that we're dealing with. And of course in this instance we're dealing with a t with 4 degrees of freedom. And it's very important now for us to find out whether or not this observed value of t is an usual and unusual value. Now that I have t and we've gotten this particular detail of getting s squared out of the way, let's go look at a t distribution with 4 degrees of freedom and find out where we are. The key question at this point in time will be, is this particular value of t a rare event? So first let's look at t with 4 degrees of freedom and then find out whether we have a rare event t on our hands. Here's t with 4 degrees of freedom. Now our observed value of t was equal to 0.8. If we were doing a one-tailed test of significance, right, if all we were interested in were improvements in the charge remaining on the batteries, then we'd be interested in the one area under the curve. So t is equal to 0.8, and we'd have the problem of determining what the area was under that particular curve. And it turns out that the area under the curve is equal to 0.234, about 23%. If we had been interested in doing a two-tailed test of significance, in other words, an average away from 28 in either direction, would have been informative or interesting to us, then we would have done a two-tailed test of significance, and we would have found ourselves getting the area in both tails of the curve, and that would have been a total area of about, well, 0.468. Okay, well, in this situation, these probabilities are so large that they're very common, run-of-the-mill, ordinary kinds of events. And so we'd feel, well, what the heck, there was nothing unusual going on here. And so the data do not contradict the hypothesis that eta is equal to 28. I wonder what the critical values of t are in this case. The critical values of t are those that leave 2.5% in the tail. One is 2.78, and the other one would be minus 2.78. They leave the 2.5% in the tails of the curve for a total area of 5% in the tail of the curve. Now what I'm going to do is take those critical values of t and use them to make an interval statement for the parameter eta. So let's return now and do that problem in the absence of any knowledge about sigma squared. It's just variations on a theme, gang. Here's how you get the limits for eta when you know sigma squared. And how do you imagine you get the limits for eta when you don't know sigma squared? Well, you have to take the critical value of t with new degrees of freedom, which leaves 2.5% in the tail of the curve. And of course, you're replacing s squared for sigma squared. So this will give you the limits on eta. If we do that for our particular problem, you'll find out that the average is 30, that the critical value of t is 2.78, s squared is 32, and n is 5. And that will give us, turning the crank, 30 plus or minus 7. So the limits in this case are going to be as follows. Here's the probability statement associated with the mean. With our attitude towards this particular statement, all values of eta which lie inside that interval are not contradicted by the data. This is a 95% confidence statement. Now, I'd like very much to show you at this point in time a geometric interpretation of this particular interval estimate you see right here. But before I can show you a geometric interpretation of this interval, and also a geometric interpretation of a test of significance, I have to spend a little time talking about reference distributions again. Okay, gang, what's the reference distribution for averages? I can almost hear you, right? The reference distribution for averages is what? And you're all chorusing, I hope, right? That the reference distribution for averages is a normal distribution located at eta with variance sigma squared over n. But when you don't know sigma squared, what's the variance? What's the reference distribution for the averages? And the reference distribution for the averages under those circumstances is a t distribution. The reference distribution for averages is a t distribution with the appropriate number of degrees of freedom, as determined by s squared. That t distribution will be located at eta just like that normal is, and that t distribution was going to be scaled by the quantity square root of s squared over n, whereas this had been scaled by the quantity square root of sigma squared over n. All right, now I'd like to construct the reference distribution appropriate for our particular example. Now when I construct the reference distribution with the normal, you all recall that the normal deviate, the distance out to the point of inflection on the curve, was equal to 1. But that's no longer true with the t statistic. The distance out to the point of inflection on the curve is not equal to 1. So I need a position on the t distribution that I know about so that I can multiply up by s squared over n and get it properly scaled. Sometimes the scaling will stretch the distribution out, and other times we'll push it up and tighten it up. But while I do know a point on the t distribution with 4 degrees of freedom in this case, I know the point which leaves 2.5% in the tail of the curve. And so what I'm going to do is construct a t distribution, a bell-shaped curve, and we're going to arrange it so that, see, that's the distance out to the point that leaves 2.5% on the tail of the curve of the t curve. Then I'm going to multiply it by the scaling parameter, s squared over n, or 32 divided by 5. So the distance from the center of the t distribution out to that position would be 7. All right, now let's look at that reference distribution right now. Now this must be terribly familiar by this time. However, this is not a normal distribution. It's a bell-shaped curve, I agree, but it's not a normal. It's a little flatter than the normal, and a little strung out in the tails a bit more. Now, what about this? Is it properly scaled? Let's locate it just any old place. Let's locate it at 35 for the moment, and you'll notice that the distance from the mean of this distribution out to the position at least 2.5% in the tail of the curve has been fixed at 7 units. So it is appropriately scaled, all right? All right, now let's do that test of hypothesis. You'll recall that the mean, the average, I beg your pardon, the average in this case was equal to 30. And what was the hypothesized value of the mean? The hypothesized value of the mean in this case was 28. So let's take our reference distribution and place it at 28. Okay? And now how do you feel about this event in light of what we see? Well, it's quite an ordinary, run-of-the-mill, common kind of an occurrence. There's nothing really terribly extraordinary about it at all. And we're seeing here the analog of the picture we saw earlier when we did the test of significance. suppose now I ask you to make an interval estimate for the mean. And so now what you want to do is think of the reference distribution free to flow back and forth and take any position it wishes, right? And how would you like this position? Let's take a real extreme one. How about, let's say, 40? How do you like the idea that the mean of the distribution is equal to 40? Well, golly, Pete, that makes the event a very rare event indeed. The event is something way the devil out on the tail of the curve, and such events happen only rarely. So that would be an inadmissible event. But you can see that there'd be a range of locations of eta which made the event not a rare event. And the limits in this case would run from, as I recall now, well, maybe I'd better look and see so I get it correct, run from 23 to 37. So the upper limit is 37. The lower limit is 23. Well, that can't be right. There's 23. There we go. And my attitude towards this interval is as follows. All values of eta which lie inside this interval are not contradicted by the data. Any location of eta inside that interval makes the event not a rare event. These are sort of limits to my degrees of belief into what eta, as to what eta is. The most believable value of eta, the best guess that I have for eta, is the average, 28. And so my belief is highest at 28, and then it sort of falls off in a rather parabolic way from here. My belief in what eta is falls off parabolically, if you will. And these are sort of benchmarks. And anything beyond that, it just stretches my belief so far that I can't stand it. And so I dismiss those values of eta. And I believe my belief in the value of eta piles up towards the center of the interval like that. These are various ways of interpreting these intervals. Now, of course, this is a 95% confidence interval, and it's interesting to see what 95% confidence intervals look like when you evoke t, as opposed to what 95% intervals look like when you evoke the normal deviate, given you know what sigma squared is. So let's look at what the 95% intervals look like when we have t. And here they are. And you'll notice something very, very interesting in this case. I want you to imagine that an experimenter has taken a fixed number of observations, say n observations. How many times? 1, 2, 3, 4, 5, 6 times. On 6 separate occasions. On each occasion, he estimates the average and then makes an interval statement. Now, he can't make the interval statement until he also estimates the variance, because he does not know the variance. In this case, s squared came out one value, just as the average came out a particular value. Here's another value of s squared, another value of the average being demonstrated. And all the way along here, you will notice that every time he makes his 95% interval statement, the size of the interval varies. Earlier, when I knew sigma squared, had I known sigma squared as I went along and did this, in every situation, if the average had come out the same, and I'd known sigma squared, in every case, the limits around the average would have been the same size, since sigma squared is known. See, that's what would happen if I had used the normal deviate. But in this case, I don't know sigma squared. I have to estimate it. Sometimes s squared is too large, and sometimes it's too small, and I get these varying sized intervals. However, gang, here's the good news. 95% of these intervals will trap eta. You have the same confidence interval. It's almost as though you were picking yourself up by your bootstraps. All the information has been taken out of the data. You've estimated the mean and you've estimated the variance, and in spite of the fact you're using estimates of both important parameters, it's still true that 95% of those intervals will include the mean eta. So we have an analogous situation to the ones we've had earlier. Well, to very quickly review, the important thing to remember in this case is that we've only had a situation of variations on the theme. We use t in place of z whenever we don't know the variance, and we have to estimate it using s squared. And that is true whether we're doing a test of hypotheses or, contrary-wise, whether we're doing an interval estimate. Okay, gang, we've come a long way. Please remember how to conduct a t test when you have an opportunity. But remember what a test of significance is like. It's a very, very dangerous tool to use. It's a particular mathematical instrument that leads to a final decision, not unlike that determined by a guillotine. And so, alas, the decisions are in, and farewell one and all.